Oh, in the previous video I forgot to explain what charge even was. In an atom, we have positive charges, protons, in the nucleus along with some neutrons which are neutral, and electrons that actually revolve, not actually though. Quantum mechanics explains the correct structure of the atom as we know till now. But anyways, this primitive model says that electrons revolve around the nucleus, which consists of protons and neutrons, and for any atom, the any uncharged atom, the number of protons is equal to the number of electrons, and the charge on one electron is equal to the magnitude of charge on a proton, though their masses are different. But since net positive charge from in the nucleus is equal to the net negative charge by the electrons, the total charge is zero and the atom is uncharged. But when we rub against two things like this, maybe some electrons jump off from one object to another, and therefore in one object there is a lack of electrons and in the other there are excess electrons. So as a result, we call the lack of electrons as positive charge, as there are more positive charges due to the protons and the electrons have gone. Okay, and the negative charged body is the one which gained electrons, and therefore it has more electrons than protons and net negative charge. Coming back to electric fields, we define the electric field vector to point in the direction from the source charge to the point where we actually measured the field. So this R, this symbol is called hat, R hat. What it represents is a unit vector, that it doesn't change the value, just gives the uh, direction, and its magnitude is just 1, and since multiplying by 1 doesn't change the magnitude, so the electric field here will have the magnitude of kq by r square, and its direction will be from the source to the point where we measured the field. But if the charge is negative, the vector reverses. Negative of a vector means the vector pointing in the opposite direction. So if the charge here is negative, then the direction of field would be opposite to that of r hat, that is towards it. Therefore we have negative charges that make fields that go towards it, and by a positive charge fields come out. Okay, that's electric fields. uh, the arrowhead represents the direction, and the length of the arrow represents the magnitude of the electric field vector. Okay, electric field lines. Note that electric field lines and electric field vectors are two completely different things, though they are related. What are electric field lines? Electric field line is a line whose tangent at a point points in the direction of electric field, and how close they are drawn shows the strength of the field. By strength I mean the magnitude of the field. Okay, so at what is a tangent? A tangent to a circle is a line that passes through only one point and is perpendicular to the radius. And if we have any general curve, we won't necessarily have a radius, and the tangent would be simply a line that is crossing the curve at only one point. That is a tangent. Okay, so over here, uh, the direction of electric field from a positive charge, we take any one point and draw a tangent to it, and the direction of the tangent will represent the direction of the electric field vector. Like this, for example, this is the direction of electric field. And note that near the charge the lines are drawn close together than farther from the charge. You can see that they are farther away than here. Okay, so the electric field is stronger here than here. this electric field vector drawn is longer than the one drawn here. It's this much and it's this much. Okay, so that's electric field lines. Note that they do not intersect, as intersection of two electric field lines would represent two directions of electric field, which makes no sense since there is only one direction of a vector. Okay, now we move on to flux. What is flux? Let us take a fluid flow analogy for flux. Consider a pipe in which a fluid, say water, is flowing, and we have placed a rectangular loop perpendicular to the velocity of the flowing fluid. Then what is the rate of flow of the fluid? It's the volume that crosses per unit time across this loop. Say in a time 1 second, the fluid would move by the magnitude of velocity. Say the fluid here moves at the rate 2 meters per second. So in per second it would move 2 meters, like this, 2 meters. And the volume that actually crossed in 1 second would be the amount by which it moved, that is simply the velocity times the area, since the volume of a cuboid is the area of base times height, so it would be velocity times the area. Okay, and as I explained in my first lecture, dv dt, before we had dy dx, we replace x by t and y by the volume, we get the volume flow rate, which will be v times a if the area is perpendicular to the velocity. If it's actually not perpendicular, then actually the water will flow through this section, through the portion that's actually perpendicular to the velocity. Like we found the uh, component of vector perpendicular to something, we can also do the same here. Consider this area. Suppose this is a, small a, this length is small a, and this is phi, then this length will be a cos phi, as I explained earlier. Then we can do the same for area. If this full area is a, then this area, which is perpendicular to the velocity, will be a cos phi. Therefore the volume flow rate will be the velocity times this perpendicular area, a cos phi. Okay, and that we represent by v dot a. Here we make area a vector by drawing it perpendicular to the area surface. Okay, that's it. No, that's not it, sorry. So that was volume flow rate analogy, and this is the flux of the fluid flow. And similarly we can replace the velocity by the electric field, and the area stays the same. So we have electric flux equal to Ea cos phi. Here we had the volume flux as Va cos phi, and the electric flux is Ea cos phi. That's it. So it's true, the flux through a flat surface with a uniform electric field. Okay, and if the surface is not quite flat, and if it's like any random shape, then we use calculus. What we actually do in principle is that we divide the surface into infinitely small flat surfaces and then calculate E cos phi dA. dA is the small surface area element, and then sum it. This long s represents actually summing, and this is called an integral, but don't worry about that. It simply means that we do E cos phi dA and sum it over the whole surface, and how we do it will require knowledge of calculus, which I will make in a further video, but forget it. Thank you.